Thank you very much. I always enjoy coming back to Bar Ilan, a place where I spent some of my best years. And so thank you for the invitation and congratulations. I spoke over lunch about Ron and Yuval, which I know them for so many years, so now I will just congratulate them once again, and I will go right away to my talk, as I assume that at the end of the day everyone is quite tired. So I will talk about what is called locally testable codes, and I will explain. This is a joint work with Iridi Nur, Shai Brown, and Shara Moses. Because we don't have time, I will not explain what is this book and what is the connection. If you will guess or will ask me at the very end, if we'll have time, I will get back to the photo. But now let's start with the talk. Wait, doesn't work. Oh, okay, now it's okay. Okay, so I don't want to assume any knowledge, it's a very elementary. I mean, the really, most of the talk is very elementary. Let FQ be the field of order Q. Usually we will care about Q equal 2. And NKD code over the field Q, but usually we will omit the Q if we work with Q equal 2. This is a sub for us. Is a linear code. What is called is a subspace, a linear subspace of the vector space MQ to the n of dimension k, and distance at least d. What we mean by distance? Distance of the code is the minimum of the Hamming distance between any two different vectors in the code. If you think about it for a second, because this is a linear code, this is the same, you can always take, if alpha and beta in the code, and alpha minus beta is also in the code, so you can take the distance to 0, which means it's the minimum of the Hamming weight of alpha, where alpha runs over all the non-zero vectors of the code. Now, the motivation for codes autocratic code is clear. We want to send a sequence of length k, but over a noisy channel. And instead of sending only k bit, we will send n bit, which is somewhat larger than k. And if we can place them of distance, of a good distance from each other, then the receiver potentially can correct mistakes. If the distance between any two is at least d, if the number of mistakes will be less than d over 2, we will be able to correct them. So now it's clear that what we want is that the ratio between k and n will be as large as possible, and at the same time, the distance will be as large as possible. And of course, it's also intuitively clear that these two things can compete with each other. And if you will insist on the ratio between k and n will be large, you will have to pay a price in t. Okay, now we are not engineers but mathematicians, so we are interested in the case of n going to infinity, which in the history of the subject maybe looked like a stupid thing to assume, because people use n equal 128, 256, but nowadays, even in practice, they're using n which is like 200,000, and 200,000 start to feel like infinity or going to infinity. So it's kind of relevant to think about such a subject. A code, or more precisely, I will use the word code, but I always mean really a sequence of codes when n going to infinity, is called good in the sense of Shannon, Claude Shannon, who really initiated all these theories something like 70 years ago, really put up the golden standards of the area, that we are looking for good codes, and good is not just, it's a technical term, which means that there exists an epsilon such that K is at least epsilon n, and at the same time, T is more than epsilon n. The standard terminology look at K over n and call it the rate, and the normalized distance is T over n. So we want both of them will be bounded away from zero. Namely, we want K and T both to grow linearly with n, and you can optimize. I won't go to that today. You can ask more than just that. But, and usually the terminology is constant rate and constant distance. So that's usually the terminology in the area of error correcting codes. And it's not at all clear that such codes exist at all. As I said, the distance and the rate kind of compete with each other, and Shannon showed that random codes, what is random codes? You look, say, at random matrix, n by n, let's say that m is half of n by n matrix over the field of two elements, and you take a random such matrix, and you take the set of solution of this matrix, then the kernel of this matrix will be of dimension approximately half of n, and we show that the distance will be also constant time n with high probability. So good code exists, and then the theory went on to make explicit examples. Let me jump right away, like 20 years later, to the work of Gallagher. Gallagher realized something which actually in current theory and practice is extremely important. He realized the importance of another property, which is LDPS. It's a pretty terrible name, but it's almost as bad as the name of this conference. P something. Nobody can remember what it means, so it's also here, LDPC, low density parity check. If C is defined by equation, namely by linear functionals in the error correcting codes area, they like to call it constraints, with bounded support. If you think about the matrix that I talked about before, it really means that the rows of this matrix have n goes to infinity, but on every row you have only bounded number of non-zero entries. And now, why this is so good? Because think about it, if the receiver is getting a very long word, a very long vector, and you want to check if it satisfies the equations. If the equations are sparse, then it will go much faster. So mathematically, you can say that C-perp, namely all the vectors in F q to the n, which are orthogonal to alpha, orthogonal with respect to this like standard scalar product, then you want that in C-perp is spanned by a vector of bounded support. So in C, we don't want to add vectors with small support. On the other hand, in C-perp, we do want to see vector with small support. And Gallagher defined this notion, and he basically said, okay, if you will take this random matrix like in Shannon, but conditional that the number of entries in the rows are sparse, only a bounded number, then still with high probability, you will get a good code. So there exists LBPC good code. Here, it was much more complicated to get explicit constructions, and it took something like 30 years till the breakthrough work of Sipser and Spielmann in the 90s, who gave an explicit construction of the so-called expander code. And this expander code are LDPC good code. This was a real breakthrough somehow. And when Dan Spielmann got an Evalina Prize, the committee praised this work of him as one of his 3 major achievements. But it's a brilliant idea, which really influenced the area. Ever since then, more or less everyone is working with them, is in some sense even the industry. But it's very simple. I want basically to bring almost everything in the next few minutes, because our work is also built on that. So let X equal VE be an R regular graph. Eigenvalue of the graph. By this we mean the eigenvalue of the adjacency matrix of the graph. Always between -1 to R. The largest one is always R, and like minus R is an eigenvalue if and only if the graph is bipartite, and all the other eigenvalues are in between. The important one for us is the second largest eigenvalue, lambda of X, and that is an easy exercise that this lambda of X is strictly less than R, namely R comes with multiplicity 1 if and only if X is a connected graph. We will say that X is called lambda expander for some lambda less than R. Let lambda be some number strictly less than R. X we will call lambda expander if lambda of X, the second largest eigenvalue, is less than that number lambda. Again, I'm talking about one graph, but what I really care, what I really mean, that is an infinite family of graphs where R and lambda are fixed. So I have an infinite family of R regular graphs. All of them are lambda expander for the same lambda. It's, again, there is a little history because it's not so clear that such graphs exist. They do exist, and even optimal in some sense. X is called a Ramanujan graph if lambda of X is less or equal, say, 2 square root of R minus 1. We don't really need Ramanujan graph, but we do have them. This is by a famous theorem of Alon and Obama. You cannot do better than this found if you want an infinite family of R regular graph for the same R. Again, it's not at all clear that such graphs exist. But a good number of years ago, we constructed such graphs for R equal P plus 1, and then Morgenstern, when P is a prime, and then my student Morgenstern constructed for prime power. Later on, Spielmann and others showed existence, though it's not so constructive, or semi-constructive, I don't know how to say it, also for all other cases. So we have plenty of good graphs. This we don't have to worry about that. And so we can continue with the Sitter-Spielmann construction of the code. And here is the construction. Let X be an R-regular lambda expander, again, on M vertices. Again, R is fixed, lambda is fixed, but the size of the graph is going to infinity. Let C0 be a subspace of F2 to the R R is fixed. I take a subspace of F2 to the R. I call it a small code. This is a code, but here the code is fixed. It's R is fixed, and I fix some subspace C0 in F2 to the R. We label the R edges around every vertex V by the numbers 1 up to R. You write the number 1 up to R around every vertex, and I don't assume any consistency, like the same edge. If I look at it from one side, can get the number 7, and from the other side, we get the number 5. Just label it in any way you want. And then look at the vector space W of all functions on the edges of the graph, functions to F2. So if you want to visualize that, on every edge, you put either 0 or 1. So what's the dimension of this space? Of course, the dimension is the number of edges. What is the number of edges of a R regular graph on n vertices? Is simply n times R over 2. Now I'm defining the code that we really, the big code, the large code. This is going to be all the functions in W such that F restricted to the link of B is in C0 for every B in B. Namely, for every vertex V, the local view of that vertex, you see, if this vertex looks around, he sees 0 and 1 on the places 1 up to R. So he sees a vector in F2 to the R. We require that this vector will be inside this small code C0 that we picked in advance. And here is the theorem of Spitter-Spielmann. If the dimension of the code, or the small code C0, is strictly bigger than R over 2, if the dimension will be like that, and if the distance of that code will be more than the lambda of X, then C will give us a family of LDPC good codes. Look especially at condition B. Condition B is the more interesting one because it's relate the distance of the small code to an invariant of the big graph, right? So that you see the distance of the code like that is some number between 0 to R. Lambda of X is also some number, not necessarily an integer between 0 to R, right? That's the second largest eigenvalue, it's less than R. So we have to arrange for this, and we have to arrange for these two conditions. These two conditions can be easily arranged. Something should be said there. And this way, we will get LDPC good code. Let me show you the proof, almost the full proof. I mean, it's so simple, it's amazing that such a breakthrough with such a what is sometimes the most difficult with code to show that this is LDPC code, here this is clear, because what are the conditions such a global function on the edges should satisfy, right? The condition is that the local view will be inside C0, right? So every equation defining the code is local. It just looks around itself, so it touches at most R bits. So this is clear. What the dimension? The dimension of a linear subspace is the number of variables minus the number of equations, right? The number of equations around every vertex. There are n vertices. Around every vertex, you put R minus these C0 equations, right? I took C0, a subspace in F to the R. The number of equations defining it is the codimension. So this is R minus dψ0. And if you make a little calculation, you see that what we are getting this number, which is constant for R. R is constant, this is constant, dψ0 minus R over 2 is a positive number. And this multiple n, which is the number of edges. Okay. The second, the distance need a little bit more, but if you would give me 10 minutes, which I will not take, I could really prove, because a full proof, but let me give you an indication of the proof. Let f in C be a function in the code. Now, what do we want to prove? We want to prove that this function, if it's in the code, has a very large support, right? You remember the distance of the code is the minimal Hamming weight of elements in the code. So what we have to prove? We have to prove that if you have a function f which is not 0, then it does not vanish on many edges, on a linear number of edges with respect to them. And here there is a simple lemma of Alon and Chang, which again, if I have a few minutes, one can give the proof, but I'll skip it. If G inside a graph X is a subgraph with an average degree L, and if this L is strictly bigger than lambda X, then the size of the subgraph is more than this number. It doesn't matter to us what is this number at this point. This number is just a positive number times the size of X. Right? Okay, so now let's apply this to the support f. We take the support of the function f, little f, call the support of it, capital F, and look at the graph spanned by this set of edges. Okay, so this is a subgraph. We need to make sure that the average degree is more than the second largest eigenvalue. Now we make sure not only that the average degree, the degree of every vertex which is inside is more than lambda x, because you remember we said that we are taking a code, look up there, we are taking a code whose distance is more than lambda x. What does it mean? It means that if the function does not vanish around one vertex, then it does not vanish on at least good amount of edges which are more than lambda x. So every vertex, the degree is more than lambda x, and therefore we can apply this lemma and we can deduce that the size of f, or the size of the vertices that f touches, is linear in M, and therefore it's also linear in N, and this finish the proof. And if you use, okay, so we have to make sure, something I promised you before, that this is not a problem, that we have to make sure that we can choose the original small code to satisfy the assumption. So if you use our Lubotzky graph, you know, the second largest eigenvalue is much less than the largest eigenvalue. If you take R, maybe not to be too small, then you can easily arrange this and you get this. Now I'm coming to the main topic of my talk. Actually not after the talk. In fact, Spillman, in his thesis, which was written under the supervision of Simpson at MIT, already in his thesis said that really what he wanted to achieve were locally testable code. He called them by different name, but let me tell you what he wanted to achieve. he wanted to achieve what is nowadays called, or shortly after that, people started to call it locally testable code. What is a locally testable code? A code in F2 to the n, again, n is going to infinity, is called Q epsilon locally testable if there exists a random algorithm A such that for every vector alpha in F2 to the n, the algorithm reads only Q random bits of alpha. The algorithm is allowed to read only Q bits out of n, Q independent of n. Q is a fixed number. I can read n is 200,000 and I allow you to read only 70 bits, and you have to decide whether the vector is already in the code or not. Well, in this way, it's not difficult to see that this is impossible. You don't have to decide that. You want to decide that he reads only Q random bit of alpha. He answers yes if alpha in the code. Then it does. It always will answer yes, and it will answer no with probability proportional, namely at least epsilon, the relative distance of alpha from the code. Let me explain. What we really want here, we want a random algorithm that maybe will not succeed 100% of the time, but will succeed 99, 0.19 with probability 99%, that if you get a vector, it can tell you whether the vector is of distance 5% or from the code. Why? You get a huge vector of 200,000 bits. Usually the kind of error-correcting codes which are reasonable to apply, let's say that they can correct it. The number of corrupted bits is 5%. If it is 40%, there's no chance they will correct. You don't want to read all the 200,000 bits and then to discover that your algorithm does not converge and you cannot correct. You want a very quick check. If you can do it, if you can read only 70 bits and get with high probability that it's close, and then you will send it to the algorithm. If not, you will ask the sender to send it again. This is kind of the practical application, but it's also extremely important from theoretical point of view. All this is a spatial case, but in some sense is the most important spatial case of what is called property testing, which is a deep area of computer science, which deals with problems like that. You have a property of something big, you want to touch only a small amount of bits, only a small part, and decide on some global properties just by checking very few bits. So it looks, so the reason that this problem, maybe let me first give a few examples which kind of inspire this type of thinking. Let's look at the following example. Let's W be the vector space of all functions from F2 to the n to F2. All functions, not linear functions, all the functions. So this is a huge subspace because this is a subspace, this is a space, sorry, that's not, this is a space of dimension 2 to the n. So that this will be other n. Let's see, now I define a code. C will be all functions, all the linear function, just the linear functional. The number of linear functionals is only n. I mean, the dimension is only n because the linear functional is determined on a basis, right? So the code is a very small, is of dimension m, which is log of n. So this is not a good code, but this is locally testable code. Why? So let me tell you, first of all, what is the test? The test is the simplest thing you would come with. Choose two vectors in F to the n, and answer yes if f of x plus y is equal to f of x plus f of y. If it's linear functional, it should satisfy that, right? So it will answer yes. If it's not linear, so here is a theorem by BLR theorem, which in a way was the starting point, I think, of all this theory already in 1993. He said that the probability that it will answer no is proportional, is greater or equal to 2/27 of the distance of F to the code. So this is a locally testable code. But it's far from being good, right? Because the rate of this code is terrible, it's logarithmic in n, not linear in n, right? Its distance is also good, but not the rate. So there are other locally testable code, and just for those who I will just mention there is the Reed-Solomon, the Reed-Muller, but all these codes do not satisfy some of the other properties. If they are locally testable, they are not good. Let me stop for a second on the so-called tensor code, which is maybe less known than the others, but that's the one we are going to use also. A tensor code is something of the following type. You take F2 to the N1, and you take C1 to be a subspace of F2 to the N1, and it should satisfy some condition which we call smooth. It doesn't matter. I mean, it's a technical condition which essentially every random code, I mean, many codes will satisfy that. That's not, that I don't want to take the time. And C2 in F2 to the N2, another subspace. And actually think about N1 and N2 to be equal, and even think about C1 and C2 to be equal. That's fine. The tensor code is a subspace of the tensor product of them, but you don't have to think about it in a fancy way. Just think about it. You take the n by n matrices, or n by 1 by n by 1 matrices, and you want that the rows will be in C1 and the columns will be in C2. This is the tensor code. It's all the n by n matrices such that the rows are in the smaller code and the columns are also in the smaller code. This is called the tensor code. Okay, now this is also a pretty good local testability, as a local testability, but not so good. Why? Because here, if you think about it for a second, you will see that it's good in the sense of dimension, it's good in the sense of the distance, but to check that the local testability is not by constant number. The test will be pick up a random row or a random column and check it. But how many bits you have to read? You have to read n bits out of n squared, which is pretty good. It's sublinear, but it's not constant. Okay? So in the last 20, 30 years, people wanted to get all these conditions together, but the basic long-standing problem was, are there good LTC with constant number of queries, which is still good. The nickname of this problem was the C-cube problem. We want constant rate, we want constant distance, and we want constant number of queries. The people at some point kind of gave up. There have been some conjecture that this is impossible. So, and then people say maybe it is possible. Some expert went back and forth, and somebody said, okay, let's give up on the number of queries allowed log. Can you get good with log number? Or maybe you insist on Q to be constant, maybe the rate will be slightly less. something like that. Why this is such a difficult problem? Because, as I mentioned before, some of the old philosophy, the old movement in coding code, so at least most of it, was usually random code is the model. We want to get something which would be maybe as good as random. But here it's not so difficult to show that random codes are not LTC. So in Hebrew, we can say it in Hebrew, then I wrote it in English. We need, we are looking here, if you know that the random codes satisfy and you want to look for an explicit construction, אז אנחנו מחפשים שחת בערימת שחת. כאן חיפשנו מחט בערימת שחת, כאשר לא ברור אם המחט בכלל נמצאת שם. So in English, so we need a needle in a haystack rather than head in a haystack, if the needle exists at all. So the good news, and that's the work I want to talk about, that there exists and there existed even an explicit construction of LTC good codes with Q constant. So this is the joint work with Iridi Nur, Shai Efram, Livne, and Shachar Moses. Amazingly, basically at the same week, two Russians, Panteliv and Kalachev, also put on the archive the construction of such codes. They came from a different point of view. Their interest was quantum LDPC good codes, which was another major problem, and they solved it, and along the way, they solved also that problem. So it's kind of amazing that the problem waited for 30 years, and suddenly things that told. Let me show you our construction. Their construction is a little bit more abstract, but to be honest, I haven't read. All this is very new for the last few weeks. So I don't want to see what the difference. There is some advantage to our method, but a small one. Anyway, let me give the construction. Here is the construction. Let G be a finite group with two symmetric set of generators, A and B. We'll put two conditions. First condition that the identity is neither in A nor in B. The second condition, which is slightly more difficult to achieve, we call it totally non-conjugate. We want that no element of A is conjugate to any element of B. Namely, for every A in A, and B in B, and G in G, G minus 1A, G is not equal to B. So A and B should be somewhat independent of each other. We can achieve this. But you have to a little bit to work for that, but it's not terrible. Okay. And we don't really need it, but let's assume that A is equal to B. The size of them, or both of them, is equal to R. And let's assume that both of them, the K graph of them, I guess everyone knows in this order what is a K graph. K graph of a group with respect to a set of generators is a graph whose vertices are the elements of the group, and you connect G with A times G, right? We both the two K graphs are both of them Ramanujan, and we have sufficient experience in construction of Ramanujan graph that we can get all this. Don't worry, Ruben, I will finish soon. This is only 2 more slides. Now, we define something which surprisingly does not appear in the literature, and we call it left-right K complexes. Let me say a sentence before defining it. Usually, when we say K graph, we can multiply, we take the group elements, we can multiply by the generators either from the left or from the right. And we usually say, okay, let's do it from the left. Or do it from the right, maybe according to your political preferences or whatever, but it doesn't matter. Why it doesn't matter? Because the two graphs are isomorphic. It's a little exercise. So we don't really care. But for some reason, you know, mathematicians are doing a Cayley graph for over 100 years, but it doesn't seem like they look at the following construction. Look at the left-right Cayley complex. Why I call it a complex? We denote it KAGB by letting A act on G from the left and B act on G from the right. Now I think of it not just as a graph. I'm going to think about it as a two-dimensional structure, which I have beside the graphs, the vertices and the edges. I also have squares. Okay, I have the squares will be the following. You start with G, you multiply it from the left by A, you multiply it from the right by B, you multiply it here up by this, the same A like here, you write here by B, you get to AGB, and this will be a square in of the graph. So for me, this left-right Cayley complex is a two-dimensional object which have vertices, edges, and squares. The condition T and C, if you check them, it's not clear that we really need it exactly. It just, if you check, it's exactly to say that all these four vertices are different than each other. Okay, how many such squares we have? That's easy to check. It's 1/4 the size of G times A times B. Now, we are going to take G going to infinity, but the size of A and B are fixed. Okay? As I said before, these are Ramanujan graphs. On R generators, R is fixed, the size goes to infinity. Now we take CA inside F2 to the A smooth code, and CB in F2 to the B some code. And okay, I assume that A is equal to B, I don't mind to take the same code, and I will look at the tensor code. Okay, the tensor code is matrices I by R. R is fixed. R is fixed, right? Okay. If you think about it for a second, then you see that, look at the squares around a vertex. If you look at the square around the vertex G, there is a one-to-one correspondence between all the squares touching G with the product A times B, right? Like there are squares touching G. And now here is my code. We can define the following. W, the full space will be all functions on the squares. So the dimension of it is like the number of the squares, which is 1/4 A times B times G. And now I ask what are the sorry, I forgot to say before. I take CACB, and C0 is the CA tensor CB, right? So these are R by R matrices. Okay, I can think of it as a subspace of the vector space F2 to the A cross B. So now what is C? My code is all the functions such that for every vertex, the F restricted to the link of G, for every vertex G, for every element of the group, I look around me and I see an R by R matrix. I want it to be inside the tensor code. Okay? And the theorem is, now so I didn't want to bother you because I'm afraid that the exact conditions, they're not too bad, but they're not as nice and elegant in the Simpson-Spielmann. But if they're very similar, under some suitable assumption on the chords and on R should be fairly large but fixed. These will give me, when G will go to infinity, ATC good chord. The proof is more difficult than Simpson-Spielmann. The beginning of it is like, it's just like Simpson-Spielmann. The dimension, the rate is just the same kind of linear algebra computation. The distance is essentially the same argument of Simpson-Spielmann. What was the argument of Simpson-Spielmann? I just repeated it, and that will be essentially my last statement. That if you think morally, the argument of Simpson-Spielmann about the distance, formally speaking, they are using the Alon-Chan lemma. But kind of morally, they're saying the following. Take a function f, assume it's not zero on a vertex. It's not zero on a vertex, and it must, on an edge nearby a vertex, then it must be non-zero around several other edges around the vertex. Okay, apply now again to each one of the neighbors of that. Right? Now go to these neighbors. It's not zero nearby them, so it's not zero more. So it's kind of expand, they propagate the local distance around one vertex to a global distance. So morally, that's what we are doing here. It's much more complicated, but it's elementary. Well, I mean, I need an hour, or maybe a little bit more if I want to do all details here. But they, again, use some more little extension of the Alon-Chan lemma, which is a little bit more, but again, it's linear algebra, which can be proved elementarily. And you propagate the local distance of the tensor chord from local to global. So we have a local distance to the tensor chord, and then we propagate it. We show that if what is really local distance? Local distance, I want to tell you that if you violate one constraint, then you violate many others. So if you violate one constraint around that, you know that you violate many others around that, and then you have to make sure that it goes and propagate all around. So there is some work to do, but the philosophy is the same philosophy. And to be honest, this work would be done 20 years ago. Maybe nobody did it, and now, okay, each time I promise this is my last sentence, but now it will be really my last sentence. We came to that with a much more fancy plan to use high-dimensional Ramanujan complexes. So Uzi is here, one of the founders of the subject, but the subject was really started by Garland in the 70s. Garland proved a conjecture of Serre about some simplicial complexes which are quotients of the Boatitz building of simple periodic Lie groups. And the way he proved it was really local to global. It was vanishing with some chorology. I won't go to that. But essentially what he told us that there is a local to global phenomenon in high-dimensional which does not exist in one-dimensional. This phenomenon does not exist in one-dimensional. There is some local to global things which make the Ramanujan complexes in dimension 2 and up different than dimension 1. It's just not just the same but in either dimension. So somehow religiously we believed that that's exactly what local testability is about, right? From local to global. And we wanted to use very fancy. Eventually, it became, we failed to do it in a complicated way. So it enforced us to do it in a simpler way. And that's the result. So that's the reason we were thinking about these two-dimensional complexes. Yeah, that's all.
Thank you very much, Alex. Do we have a question? Yeah.
This construction looks similar to the zigzag product from the small.
Yeah, there is a famous construction of expanded graphs by the so-called zigzag product. The zigzag product have this type of phenomena that you have big and small, but you always stay in a one-dimensional. I actually don't know. It might be that either I don't know that the zigzag was before Simpson's Spearman or after. After maybe the zigzag was influenced from the Simpson's Spearman, but the two-dimensional in a way the novelty of our work is to say think two-dimensional instead of one-dimensional, and I can elaborate a bit more in a heuristic way. I can even prove in some sense that graphs, at least some properties like that of graphs, are not local. You cannot recognize them from local. On the other hand, in the high-dimensional, you can recognize global properties from local characteristics.
More questions? More questions from home? If someone wants to ask, just unmute and ask.
We speak Peter.
And see.
Peter Winkler. No.
Maybe an easier question.
Yeah.
The groups A and B and group G can be any abelian group.
No, not a billion. A billion group are never expanded.
So
are never. The groups here are PSL2Q, where Q is a finite field. The size of it goes to infinity. No, a billion groups will not do it. A billion groups are never expanders. They either have to be Ramanujan or at least very good expanders.
And SN
or what? SN. Okay, SN is an interesting story. SN, we know to make SN into expander. This is the famous book of Martin Casaro. But here we need more than expander. Expander tells you that the second largest eigenvalue is less than the largest minus epsilon. We need it to be sublinear. So sometimes you can arrange it, you can start with this and you can enlarge the set of generators and you achieve it. So maybe it's possible to do it with SN, but it needs some thought.
You can take a power.
What? You take powers and then you can make it probably by paying a fairly large price on the R, but if you don't care, I guess you can do it. Yeah.
Okay, any other questions? Okay, if not, so let's thank us again. I would like to thank all the speakers today. Thank you, and the organizers for this very nice conference and this very nice handling of the pretty difficult situation. Thank you very much.